nice things that are going to let us write less boring code. The first talk is going to be presented by Ryan's code about the new deriving mechanism we just showed in GHC.
All right, can everybody hear me? Excellent. Okay, well, today I want to talk to you about this cool thing which has just landed in GZ 8.6, just came out earlier this week, called Deriving Via. As the name very suggestively indicates, it lets you derive instances of type class via other type classes. That's pretty cool. My co-authors and I developed this after we noticed that there were certain patterns of type classes that we kept writing over and over, and despite all the machinery that's in GEC, we couldn't figure out a good way to automate it. So that gives some of the context for why we decided to go down this route. To give you a flavor of what Deriving Via is, before I dive into the heart of this talk, suppose you had this data type pair, that's a new type around 2 ints. Here's a mono instance we might conceivably write for this. Notice that we're taking the left thing in the pair and combining that by way of addition, and we're also taking the second thing in the pair and combining that by way of multiplication, as indicated by the blue and orange colors. So this is an instance that you can write. It's a little bit tedious, but it's perfectly possible to do. But luckily, we don't have to write this anymore. Now we can say deriving monoid, and we can now say something after the deriving clause via sum int and product int, where sum and product are new type adapters that give you the properties of addition and multiplication. So that's really cool. Now we don't have to write boring instances like that anymore. And if you don't believe me that this works well in practice, I guess I can give you some unscientific empirical evidence here. So this is a very large production Haskell code base, as evidenced by the name Haskell Mega Repo. And one thing to note here is that the only change that was made in this was just to replace instances with their deriving via equivalents. And that alone saved about 400 lines of code in itself. So this thing seems to work quite well in practice, if you didn't want to take my word for it. So I've chosen those examples and all the lines of code you can save. You might get the impression that this is somewhat magical and mysterious, which is understandable. So it's my goal here to try and demystify this and explain what's underlying this. And there's essentially 3 things that make this tick. Of course, there's the deriving keyword, because we wouldn't be able to have that without deriving the name. And we're also going to make important use of new types here. New types are going to be like the thing that lets us insert some custom behavior whenever we're trying to reappropriate type class instances as we see fit. And we're also going to make use of this thing called coercible, which isn't quite as widely known as deriving in new types, but I will explain that in due course and explain how these 3 things fit together to make one cohesive product that we call Deriving Via. So to start off, let's take a brief glimpse back into the history of deriving. This has been around since at least Haskell 98, where they put this in here as a convenient shorthand for deriving instances of some commonly used type classes from base, like eq, for, show. And pretty much stopped there and figured that would be all that it would be useful for. But as luck would have it, people started finding uses for this well beyond the scope that was originally intended for deriving. So after this was introduced, we started developing language extensions to increase the expressive power of deriving. So on top of that, you could derive instances for some other type classes in GHC. You could derive instances of type class separate from the data type definition. You could derive instances for any new type. You could derive instances where you don't fill in any implementations to let defaults kick in. And even more recently, you can derive instances where you can say at a finer granularity what kind of approach you want to take when generating the code. So there's all sorts of wonderful language extensions. But despite all this, I'm going to claim that deriving is still somewhat impoverished today. There's certain predefined boxes that these language extensions let you fill your code into. And if the kind of stuff you want to generate doesn't fit into one of these boxes, then you're basically out of luck and don't have much alternative except to write the instances by hand instead. And that's unfortunate. So let me give you an example of one of these kind of situations that we started running into. So I'll motivate this example with 2 type classes, monoid, which describe how to algebraically build up and combine things, and applicative, which is a particular way of sequencing effectful actions. And I know here I'm going to be using this pure lift A2 formulation of applicative. You'll see why in a bit. So here's an example of a monoid instance that makes use of those two type classes. So for the monoid instance for IO of A, what you do is you take some monoidal thing A and lift it into IO, which is an applicative context. So for mempty, you take the mempty type A and lift it with pure, and then from append, you take appended type A and lift in IO of A using lift A2. And as it turns out, this sort of pattern also works for the ST type. Nothing too surprising there, I suppose. And this pattern also works for functions. And this pattern also works for pairs. And if you keep going, you'll probably start to see a pattern here. Of all the slides I just showed you, the types at the top change a little bit, but the implementations remain exactly the same. So this is a pretty clear sign that there's some sort of abstraction to be lifted out here and reused. So let's see if we can do this. So all those instances basically share this kind of pattern. You have some applicative F, monoid A, and then you can come with a monoid for F of A by using the code below. And this is a thing that you can define, and it works okay in isolation, but when you start adding more stuff into your Haskell universe, then it kind of topples over. The reason is because this isn't the only way you can define monoids for F of A. Here's another perfectly valid way you can do it by way of the alternative type class. The details aren't terribly important, except it's distinct, and it's appropriate for different situations than the instance on the top of the slide. And unfortunately, we cannot simultaneously have both of these things, because when GC looks up instances, it only looks at the instance head, and both of these are headed by F of A, so therefore they overlap. So we can't have nice things in this fashion. So if we want to have nice things, we'll have to get a bit more creative. So the usual way forward here to avoid overlap is new types. New types are just a convenient way to get something which has the same operational cost at runtime as an underlying type, but give it a different tag that you can attach instances to. So here's an example of the app new type, which also is going to be released in the next version of GHC, 8.6. One thing that you can do with app is give it the mono instance that we tried to earlier, except this time now we have app at the top, so no other overlaps. And also in the implementation, we need to sprinkle in some uses of app new type constructors. But otherwise, it's the same code. So with this, now we can try to revisit our earlier instances and eliminate the applicative boilerplate that we saw. So returning to the monoid instance for I/O, instead of using pure libk2, we're going to try using the app new type. And here's how you accomplish that. So notice that mempty and append didn't change here. They remain exactly the same. But now we're using the underlying monoid instance for app to accomplish our goal. So great, now we don't have to copy and paste the applicative boilerplate into every instance that we use. So problem solved? Sort of. We sort of lost something in the process, because if you compare the code on the previous slide and the code on this slide, there's actually more code than before. So clearly we've lost our way here, and we need to rethink about how we do this. So in an ideal world, we wouldn't go and have to put all of these apps in ourselves. We could say something more declarative like this. You could just, at the definition side of IO, you will say deriving monoid via app IOA, and have it just fall out automatically. So that's going to be our goal today, and I'm going to show you how to make that possible. So I just explained the roles that deriving and new types serve in this kind of general framework. The one thing I haven't explained yet is this coercible bit. So let me take a brief segue and explain what coercible is and the kind of thing that it lets you do, and then we'll segue back into the conversation of deriving via and show how coercible powers it. So to be perfectly clear, coercible is not a new idea that we introduced in this paper. This has been around since this safe zero-cost coercions for Haskell paper and debuted in GDC 7.8. So not a new idea, but you don't have to have read this paper to understand the talk. The essence of coercible is that it's a special constraint that GDC provides that witnesses the fact that two types have the same runtime representation. So you can think of it as like a broader notion of equality than actual equality. And the thing that really makes coercible really flexible is that we have constructs in Haskell which have equal runtime representation. They're called new types. So as one example, I'm going to define this age new type, which is a new type around int. And if we define this, then we can state some facts about coercibility with it. So because age is a new type around int, we have this coercible age int constraint in the scope. And I'm using the word instance here to describe what it looks like, but you can't actually write instance of these by hand. This is something special that you see in the scope. And because coercible is an equivalence relation, you also have the symmetric direction, so you also have coercible age int available to you. And another important property of coercible is that you can lift it through other type constructors. So as one example, you can take the arrow type constructor for building up functions, and you can lift the fact that age is intercoercible to int through it, so you can get that age to bool is coercible with int to bool, and vice versa. And that's a property that's going to become important very shortly. So now that we've talked about how this works in the types, I need to tell you how it actually works when you hit the ground running at the value level. So the place where coercible really becomes important is this coerce function, which takes some A and casts it to type B. So this bears a striking similarity to its less well-behaved cousin, unsafe coerce. But importantly, because we have this coercible constraint at the front, this ensures that they're going to have the same representation at runtime, and therefore it can't go wrong. So coerce is actually type safe as opposed to unsafe coerce. So here's an example of where you might want to reach for coerce. So returning back to the age example, suppose you define a successor function over both the ints and ages. So a successor event is very straightforward. You just add one to the arguments. And then for successor of age, what you first do is you unpack the new type constructor, extract the underlying int, take the successor of that, and then package it back up with age again. So this is one way to implement it, but it's a little bit tedious because you have to use these age new type constructors in various spots. So what we can do instead is just wipe all that away with coerce. And recall that this works because we can lift coercible instances through type constructors, which, because a int is intercoercible with age, this lets us conclude that int to int is intercoercible with age to age. So we've accomplished two things here. One is we've come up with a shorter implementation of this function, which is this kind of nice in itself. But another thing that we've done, which is even nicer from Deriving Via's perspective, is that we no longer have to think carefully about where to put new type constructors when we're implementing these things. And for successor of age, it's not terribly difficult to figure this out, but you can imagine as you get into more complicated examples that this would be somewhat tedious to implement and automate. So coerce relieves us of that burden. All we have to do is just give something to the constraint solver, and GEC is quite good at figuring out those sorts of problems. So now that we have coerce, I can finally explain what kind of code that this generates underneath the hood. So when you say something like deriving monoid via app IOA, then behind the scenes, this is going to be the instance that it generates. So once again, we're no longer explicitly appealing to the applicative methods here. Instead, all we have to do is, when implementing memd append, call memd append at the type after via, which is app IOA, and then use coerce to cast that to the appropriate type for the monoid IOA instance. So for memd it would be IOA, and for the pen it would be IOA to IOA to IOA. And note here that the reason that this works is because we have modified evidence that IOA and app IOA have the same runtime representation, since app IOA is a new type around IOA. Very good. So now we have a general framework for implementing the code generation part of Deriving Via, and this lets us very neatly explain how this works without too much hassle, as it turns out. The algorithm underlying Deriving Via really isn't the most remarkable thing about it, in my opinion. In my opinion, the thing that really makes it shine are the various applications that it can be used for. Because although it's simple to explain, some of the things it lets you do are pretty amazing. So I'm going to give you a flavor for the sorts of things that we have found while playing around with Deriving Via, and hopefully this will inspire you to find some other use cases of your own. So one thing that's I just love to point out to people is that Deriving Via is actually a strict generalization of the generalized new type deriving language extension. So much so, in fact, that we briefly considered calling this generalized new type deriving. That was a bit of a mouthful, so we decided to shorten it to Deriving Via. To see how that works, here is using the deriving strategy syntax, an example of generalized new type deriving. So here's how you would use that to come up with a num instance for age by reusing the num instance for int. And you'll notice, if you stare at this code, that there is a striking similarity to the code that I just showed you for Deriving Via. And that's not a coincidence. You can just as well express this sort of thing by using Deriving Via and saying deriving num via int. So what does Deriving Via give you on top of generalized new type deriving? Well, for one thing, it lets you specify in greater precision what kind of data type you're reusing the instance from. So unlike for new types, you're no longer limited to just picking one particular type to steal from. And another thing to note is that Deriving Via is not limited to just new types. So this technique also works for deriving instances for data types in addition. And also, one other language extension that Deriving Via sort of improves upon and makes much it provides a nicer framework for explaining, I think, is the notion of defaults. So there's this language extension called default signatures that kind of gives you the most advanced way to declare defaults at the moment. And I've used this in a lot of places, but it's never quite sat right with me for some reason. I couldn't explain why until Deriving Via came along. So let me explain what I mean by this. So imagine you have some type class for pretty printing values, and it has a method pprint for turning that value into a pretty printed document type. So as it turns out, most instances of pretty are pretty predictable. So we can come up with defaults for this pretty easily. One sensible default that you can pick is reusing the show type class. The show tells you how to turn things into strings. It might not necessarily be like the most well-formatted or necessarily pretty output, but it's a sensible thing that you could do. So here's how default signatures would let you express this idea. You could say, if you can, if the value happens to have a show instance, then you can implement pprint by first showing that, i.e. converting it to a string, and then turning that into a document by way of this text combinator. And then to actually use it, all you have to do is come up with the data type of the show instance, and then simply implement an instance of pretty foo without filling in any implementation for pprint, and then GHC will fill in the default for you. So this works great, but as it turns out, this isn't the only sensible default you can give for pprint. Another thing that you might want to do is use a generic-based default, because maybe show doesn't quite cut it for you, and you want to configure it with data type generic programming. So let's instead replace show with some generic stuff, and then we can implement an instance for pretty using generic. Okay, well, now we have a bit of a problem because there's two ways that you can define it, and in certain contexts one works better, and in certain contexts others work better. But default signatures doesn't really let you work with this because it forces you to pick one particular default and to couple it with the class definition. So if you have something with both show and generic instance, then you have to figure out which one is better. And that's not really satisfying. So what I'm going to propose is that we forget about default signatures entirely and come with a better solution using Deriving Via. So the way we're going to accomplish that is just first declare pretty without the default signature, and then come up with these two new types, which I'll call show pprint and generic pprint. And the reason I gave them these names is because we're going to give them instances of pretty. For the pretty instance for show pprint, we're going to inline the show-based default, and for the pretty instance for generic pprint, we're going to inline the generic-based default. Once we have these in place, then if we want to come up with a derived instance of pretty for the foo data type, now all we have to do is say deriving pretty via show pprint. And this is preferable for a number of reasons. One is we're now much more explicit about the default we're using. So people who are glancing at this code can now tell much more easily what kind of code is going to be generated behind the scenes for you. And if we don't want to use show preprint, then switching to the generic default is just a matter of swapping out show preprint for generic preprint. So now toggling between these two things is extremely simple. So this is great because now we no longer have to couple defaults with class definitions. And one thing that this enables is now we can have people who don't have push access to the original library. They can define their own defaults of other libraries and expose those to users. So now we have a way to make defaults more first class in some sense. So this has led me to come to the conclusion that perhaps we should be doing this instead of default signatures almost all the time. And gosh, there's all sorts of crazy things that you can do with Deriving Via that I would love to be able to tell you today, but unfortunately I don't have the time, so I'm just going to briefly mention them here. So one thing that I show is that in order to derive something via another thing, they have to be intercourseable. But strictly speaking, that isn't true. If you borrow techniques from data type generic programming, then you can basically expand the equivalence classes of things that are intercourseable by using the generic type class. So that's talked about in the paper. Also, it's worth noting that this interacts quite well with existing GEC extensions such as standalone deriving, associated type families, multi-parameter type classes, and other things like this. And then also we go over some other interesting applications of it that are worth reading in their own right, such as a quick way to say how to derive asymptotic faster code, and also as a technique for retrofitting superclasses. You can imagine that Deriving Via was around when the applicative monad proposal was being debated, then it might have eased the migration story there. So that's some stuff that I will just leave off there. All right, and that's basically everything that I wanted to mention today. As I mentioned before, this just debuted this week, so I encourage you to download GEC 8.6 and try this out and come up with crazy ways to delete all the code in your libraries. And yeah, just as when Deriving Via was first envisioned, people came up with use cases of it that are well beyond the wildest imaginations of the people who wrote the Haskell report. And similarly, I think we've only scratched the surface of the kind of things that you can do with Deriving Via. So it's my hope that we'll get to see more creative use cases and more ingenious constructions. So with that, I will turn over the floor for questions. Thank you.
The example you had for all these type classes, for types kind star, does this make sense for type classes that are for like star to star GDS? I wasn't quite sure what the course into at that time.
Okay, so the question was, does this make sense for deriving instances for data types where the kind isn't star, but something like star to star? And the answer is yes. I didn't show any examples of this in great detail, but you can derive instances of functor via some other thing, like you could define a new typer around maybe, and then derive a functor instance for that via maybe or via something which is representational equal to maybe. And in the paper we talked about the kind of like type, we apply some like kind checking when we're type checking Deriving Via to make sure that the kinds actually align up in the ways you'd expect, so that you don't have the ability to write things that are total nonsense.
It seems to me that with usual defaults you can specify a per field default. With default via you have to do it for a whole class. So can you comment on that? Because it seems to me that your extension is not really an extension of default signatures per se.
Right, so the question was, with this technique, when you're employing default signatures, you have to do it on sort of a whole class basis, whereas normal default signatures lets you give defaults for particular methods and then give you the ability to define only one method at a time and let the others fill in based on that. And yes, this is admittedly a weakness of the system, which is why I was careful not to claim that this replaces default signatures, but rather improves it. I get to come up with a really nice encoding of a way to achieve the same sort of per method defaults. But I think with enough elbow grease, you could probably come up with something that looks essentially really close to it. You know, the good thing about this technique is it lets you encode stuff at the type level and the type you give after via. So I can imagine you might be able to emulate something to this effect with some type level voodoo.
What besides the placing the via tables, can you place type under? Does it have to be type
The question is, what sort of types can you put after via, such as one example, can you put type families after via, or does it have to be a data type? And the answer is, I believe you can put any type whatsoever. We're piggybacking on top of GAC's existing type checker. So if you put type families in there, then in theory they should normalize if that's a well-defined thing to do there, and you should be able to, you know, abstract away with type families, assuming that they don't get stuck at some point. Because if they got stuck, then you'd be generating an instance for a type family under the hood, and that's not something that GAC prevents.
Is there an effect on compilation time for better or worse compared to other deriving strategies?
The question is there an effect on compilation time for better or for worse compared to other deriving strategies? And the answer is no, as far as I know. It essentially does the same code gen strategy as generalized new type deriving with some extra bells and whistles on top. So I don't have any empirical evidence to back up this claim, but in my experience, there's been no source of compilation time for when using this feature heavily.
If anything, I would guess it would be better.
Yeah, I mean that's kind of the nature of zero cost coercions, right? That they're zero cost, so they work quite nicely in that respect.
Okay, let's bend the speaker one more